Namaste and welcome everybody. Today we are going to present as a team. It's a teamwork, and between two institutions. Uh, our group here at UNSW, Transitional Artificial Intelligence Research Group, and we have the Center for AI Innovation, Pingala Institute, and Dr. John Hawkins from there is with me. So the topic is recursive deep learning framework for forecasting the decadal world economic outlook. Um, John will take over the presentation first.
Awesome, thank you, Rohit. So, just an overview here. I'll introduce, do this introduction, hand over to Rodney to give you some background material about GDP and forecasting. Then I'll talk about our research goals for this project, the GDP data, some of the pre-processing that was done with that for the task. I'll then go through the different methods we use, giving you an overview of all of those, then hand over to Rohit, who'll talk through the deep learning framework for doing the large-scale forecasting. He'll talk about some of the results, focusing on Australia as well as the other countries, and then move to conclusions. So the kind of questions you might ask straight away on this when you look at this topic is, what is GDP? Why do we want to forecast it? And how is it traditionally done? So I'll hand to Rodney to talk through that.
Yeah, okay, so GDP is basically the total monetary value of all final goods and services in a country. So it's what consumers are paying based on that definition. But there are different ways of measuring it. There's a so-called production approach, which basically takes value added and then sums up the value addeds or the production values. But also you need to avoid double counting, because if you just sum up the value of production for all firms, the prior firms have to be netted out to get the value of the final goods and services. The other approach is the expenditure approach, which is to sum basically consumer spending, and an income approach, which would also include, so you sum up all the incomes from all the businesses, but it also includes things like dividend payments, because businesses are in the end owned by consumers. So these are sort of the three main approaches. They should result in the same numbers. There is some statistical error when you look at the system of national accounts. There tends to be sort of statistical errors that appear in there, sort of rounding errors. But other than that, they result in the same approach. Now, why GDP? Well, we're interested in it as a macroeconomic indicator, along with things like employment, consumer price index, interest rates, etc., because it gives information about the status of the economy. The growth rate gives us information about whether we're in a recession or not. So 2 quarters of negative growth is the typical recession indicator. And in our case, we won't have that because we're dealing with annual data. The other thing to mention here is the people who use this sort of work would typically be things like credit rating agencies, banks, central banks in particular would do this type of work. They're the ones who are really interested in this, and it becomes part of sort of the general debate about how well the economy is doing. Standard methods that have been used by macroeconomists, typically they might use autoregressive integrated moving averages, ARIMA, vector autoregressions, VAR, VECM, vector error correction modeling, when you're looking at co-trending series that may not be stationary, then you're looking for long-run equilibria between different series of data. And the other method they tend to use, particularly in the central banks, which has become widespread, are dynamic stochastic general equilibrium models. These are more a theoretical model, which is then estimated using statistical methods, often Bayesian methods, to sort of estimate the major relationships between the different macroeconomic variables. So that's an approach which mixes optimization, so economic optimization and statistical modeling. So we don't do that comparison because that would be a massive project to try and look at that. Next slide, please.
I think that's me, Rodney.
That's you? Okay, over to you.
So I'll just quickly summarize because it was a little bit faint here. GDP is a macroeconomic indicator that gives you an indication of the overall health of an economy by measuring the amount of economic activity. It gets used by all kinds of policymakers as well as, say, macroeconomic investors who want to understand how the economy is functioning and how it will continue to function in the future. And there are specialized time series statistical models for doing these kinds of forecasting. We're benchmarking against several of these. So I put a slide in just to talk a little bit about what we mean when we're talking about time series data, because there is some terminology that you may not have encountered. Here's basically the percentage change in GDP, so GDP growth over time for Australia. And typically what's very special about time series data is you're usually making predictions using time lagged values of the value itself. That's what we refer to as autoregressive, auto meaning onto itself. You're looking at previous values for the thing that you're trying to forecast, sometimes also called an endogenous variable. There's also exogenous variables where you include additional time series data, which we're doing in our work. Those essentially meaning those are variables that are outside of the thing you're forecasting. And we separate between those two when we're talking about the definitions of these models. So the research goals for this project were twofold: benchmark traditional forecasting against machine learning approaches, and then apply this to a large-scale recursive method for doing long-term decadal forecasting. The data itself, we chose to 13 different countries. So the G7 countries, which includes large first world nations, as well as what are called the BRICS developing economies of Brazil, Russia, India, China, and South Africa, plus Australia, because we're here and we want to understand our own GDP. The source data comes from a source called the Penn World Table, which, as well as the GDP data, also contains multiple exogenous variables, including population growth, CPI, etc. It's worth noting that we took the data from 1980 through to 2019, so a 39-year period, so that we'd have the same years for all countries. The only exception to that was Russia, because it only had data from 1991 forward. That data gets processed. First of all, we do differencing, so it's we convert it to a growth rate percentage, and in most of the models we're looking at differencing. But we process it into two windows. There'll be an input window depicted here by X1, which is basically the number of time steps you're looking at in order to make it a prediction. And Y1 is the period of the forecast. So you'll be predicting the GDP multiple years into the future. So M here is the number of time steps included in the input features. N is the number of time steps in the output, like how far into the future you're predicting. The traditional methods, so Rodney mentioned before the ARIMA model. So the AR in ARIMA stands for autoregressive, meaning that it uses its own time-lagged versions of itself. That is usually parameterized by a value P, which indicates how many time steps into the past you're going to include into the model. The integrated component actually refers to the number of times you difference the data against itself, because the assumption of this model is that it should be stationary, meaning that it's got a constant mean and standard deviation. So effectively, that's not in the formula. There's a process in fitting in ARIMA to determine how many rounds of differencing you need to do in order to make the data stationary. And then the moving average component refers to the terms at the bottom there, where you include you have parameters over the observed error of the model previously. So as you're applying the model moving forward, you record the errors it's made in previous predictions, and you have a parameter that fits adjustments for those historical errors. And that the number of time steps you use that for is parameterized by Q. So that P and Q you'll see later, we will fit different parameters of those depending on the data we're looking at, and they're not necessarily the same value. The VAR model now explicitly introduces exogenous variables. So typically what we're seeing here is to make a prediction YT, here is a vector, you'll have some vector of exogenous variables X, it's parameterized by B. And then just like in the previous ARIMA model, then there's multiple time steps of the endogenous variable that you're fitting parameters A1 through to AP. That's the VAR model. I'll move now into talking about the deep learning models. So there's 4 different deep learning architectures we applied to this, starting with the first 3 of which are recurrent neural network architectures, the last of which is a sort of feed-forward architecture. The long short-term memory is a type of recurrent network. So if you look just at the top of the diagram to begin with, what you're effectively doing is you start with processing part of the input sequence. It gets processed through a cell, generating a hidden state. It could potentially produce an output at that point, but in a lot of these problems, what we're doing is we're continuing to process the data until we get to the end of all of the known data before we produce our final prediction. And what you'll see is that in a standard recurrent network, if you can see my pointer, it's just the activations of the hidden nodes that are passed forward. But the LSTM architecture was designed to deal with multiple problems of standard recurrent networks, namely the vanishing gradient problem. You want to be able to propagate error backwards in order to deal with that problem. And it does that by introducing 2 different values that are maintained through time, the state of the model as well as the hidden activations. And this diagram here looks very complicated, but it's actually just saying that you are going to, there's what's called a forget component. So you adjust the hidden state based on the current input in order to forget some of those activations. There's an input component where you say, okay, do we want to add something to the internal state? And then an output component where we learn how do we want to modify the hidden state and the next hidden node activation based on the current input. So that's the basic unit of the LSTM network. Worth noting that all of this is parameterized and back-propagated against to learn, except for the X's and the pluses. There's no plus in that one. Those are simple matrix operations. So the next architecture we used was the bidirectional LSTM. So this is an extension of the previous model where, so if you think before, the F cells is the forward LSTM model we used before. We were basically processing the input chunk by chunk until we get to the end and produce our final output. In the bidirectional, you run a second LSTM model from the end of the sequence through to the back of the sequence. So these things are running in parallel in different directions. What typically happens is you take the hidden activations at the very end for each of the 2 networks and then propagate them through a feed-forward neural network to produce a final output. And the idea is basically this forces you to end up, the standard LSTM processes the signal moving forward, and it still tends to overemphasize recent data in the series. The backwards step will push back and give you more information about what happened earlier in the series, and then you kind of learn which of those is most important in your final activation layer. The next model we used was what's called an encoder-decoder LSTM architecture. So this was a variation of the LSTM that was designed specifically for translation tasks. So what you're typically doing is you have an LSTM that processes your input sequence. It could be English, for example, in this case, that generates a final state, and then you want to use a second LSTM network to decode that into some target language, could be French. So even though this was originally designed for language translation tasks, you can reuse it for time series by saying, oops, you first encode all of the time series that's currently been observed, and then in the decoding process, you're continually projecting forward in time all of the steps that you want to project, that you want to make predictions for. That's the encoder-decoder. The final architecture was a CNN architecture. So this is not recurrent. This is a process where you basically run what are called convolutional layers. These are effectively filters, multiple parallel filters that get run over the entire time series. And then they get compressed through what's called a max pooling layer, and then a final feed-forward network to produce the output. So this relies on having a kind of fixed length input, but what effectively you're doing is you can think of these as feature detectors. You're trying to detect many, many different features across the time series data. We used 64 of these in our work, and then that's used to predict the final output, which is a vector of predictions into the future. I can now hand to Rohit to talk about the deep learning framework.
Thanks, John, for excellent overview about the different deep learning models that we are using. So our deep learning framework, basically by the term framework, what we mean is that we use all these models and give a general setup where the models are evaluated at different stages, and then we want to use the best models later, best model later to predict the decade ahead prediction, right? So how we begin is through the by first we are our framework is not looking at is looking at different countries independently, right? So when we select a country, we do not consider the data about other countries, right? So, but we have a set of features such as the CPI, CG, macroeconomics, and labor. This is all for a particular country. So, for example, we started this process with the UK. In the PWT data set, we are looking at from 1970 to 2019. The reason we are selected till 2019 is firstly that we didn't have data, more recent data at that time, and that this project was done during the peak of COVID-19, right? So, and we did not want to include COVID-19 in this because that was a major world disruption in the financial market. So, of course, the basic is that you have a training data set and you have a test data set, but the question is, how should you develop the training data set and the test data set? And that depends, like you could separate the data by years, like you can say, okay, we are using the first 2 decades as the training set, and then we are going to use the next 2 decades as the test set, right? But that would be having a bit of a bias in the sense that you have these GDP growth trends that are more biased towards certain years and decades due to certain events happening in those time periods. So another way is that you shuffle the data. By shuffling the data, it could mean that you are looking at, you have these data segments or the windows, right, that John showed earlier. We have this data segment, so that's a window that's shown here, and basically you are creating a data table with these windows, and in that data table you are shuffling the train and the test set. So your test set may have some of the post 90s data, some of the 70s data, and 2000 data. So that range, or 2010 range. So, and the test set would be having similar. So it depends how you shuffle it. So the model training is that we are not sure what model is the best, right? And although our framework is geared towards deep learning, we also, one of our goals is to compare the results with the ARIMA and the VAR models that econometricians use. So this is essentially going back here. What we see here is a univariate signal. So it's a univariate time series prediction example. But our example actually is using, our data set is actually multivariate. So we are using all these features here in a time series. So you can think of it as having several of these lines here as an input to predict the GDP rate as the output, right? So that's what is the prediction, the GDP rate. And then we have model training and evaluation, and we select the best model. So the top part that you see is standard in applying machine learning models for financial problems. And we have done in our group, we have used Bayesian neural networks to predict the stock price, for stock price prediction, including the COVID-19 data set. And about 10 years ago, I was also involved in other financial stocks forecasting with different types of recurrent neural networks. And there's a large volume of literature where deep learning models are used for cryptos and others, and we have also done that in our group. But what is more novel in this project, and this is inspired from our earlier work, this project, the novel part is that we are taking, for example, what we are doing multi-step ahead prediction. So that step ahead is that we are, for example, looking at the last 4 years to predict the next 3 years, right? But we are not only interested in the next 3 years, we are interested in the whole decade, right? That's 10 years. So what do we do then? So we have to take the best model, right? And then we have to extend it in a recursive manner. I just want to note that time series prediction, there are two major directions in time series prediction. One is single step ahead prediction, another is multi-step ahead prediction. Two major problems that are defined, right? But in a multi-step ahead prediction, you have to be realistic on how many steps you can predict ahead. Now, what the data that we are having, it's a GDP forecasting data, right? And it's not much data. It's a limited data problem because we just have yearly data, right? Yearly data, and it's just from 1970 to 2019, right? So it's a very limited data problem for these very large deep learning models, right? So there's going to be a lot of bias. That's one thing. So we had to be careful on how we construct our data windows, basically. And the windows, if we had like 1,000 years of data, then to predict a decade ahead is kind of doable. But our data is less than 50 years, right? So we are going to do a multi-step of a few years, and then we are going to use that predicted data. We are going to feed that back into, so feedback of the predicted M steps back into the model to predict the future steps. Now, it sounds good in theory. That's what I told Tianyi Wang, who is the first author of this paper, who did his master's with us. But then he's like, what? This is not a single univariate problem. This is a multivariate problem. I'm like, oh, now we are in trouble. So we had to first train other individual models to predict features. The prediction is not the GDP rate, but the CPI, CGD, per capita, macroeconomics, and labor, because those are the features are not available, right? When you are going to predict post 2019, we have the data till 2019. We did our train and test set. We know what good model is. Then post 2019, what do we do? So in the process of predicting the GDP rate, we first have to find what is the labor rate. What is the employment kind, like what are some of the macroeconomics factors looking like? What is the CPI, the consumer price index, right? So then using those, we will get the GDP rate from 2020 to 2030. Then we look at the trend for the different countries, right? And compare the trend. And then what happens next? The final part is to look at some other forecasts, such as the Lowry Institute, IMF, and other places, right? So I think I have said all the things that's written in text later. That we are having, sorry, my bad, the data in here, 1980 to 2010 and 2011 to 2019. So this is one strategy of the train test. We are not really specifying what is the best strategy in here. So you could use this strategy, but note that this strategy may have some biasness. And the other strategy is that you can use a shuffling strategy. And in the recursive part, we are looking at predicting 2020 to 2030, right? Some of the points to consider. Developing countries have more stable economic environment, developed countries, and that's why they are called developed countries. It's not just that buildings are all developed, roads are developed. There's transparency, there's accountability in the financial processes. And that's why people trust the developed countries when it deals with money. I'm not saying that they are not prone to problems. There could be problems. There could be problems from leadership and all those things. You could have, For example, in the case of US, you have one of the major problems in the world, gun control, gun issues and all that. But still, despite that, their financial systems are very secure. That's why the US world is still using the US dollar, right? So inflation, employment rate, and other major economic indicators do not really change that much. So a developed country, actually, you could think of it as a system that has converged, right? So there is less. A developed country has less development, right? And it's the reason it's developed already, so of course the infrastructure development will be less, and because of that the growth rate generally of developed countries will be less, right? So when that's why when IMF and other World Bank, they do their forecast, they always keep the developed countries separate, they keep the developing countries separate, right? And it's understandable that developed countries having a low growth rate is okay as long as it can maintain itself, it can maintain its workforce. It doesn't need to have such a huge growth rate. If it has, there could be some problems as well. And we've seen that in the case of US recently, right? Because what US did, they started printing a lot of money, taking a lot of loans all of a sudden, right? And economics is like you cannot, money does not grow from trees, right? And when you cheat the system, you are going to have problems in the system. And there are some other African nations, they try to print their money, right? And they had problems. There's another case of Venezuela, which is more in the developing country case, which had problems as well. So now we look at the case of developing countries. They're defined as countries that are still exploring path of national development. There will be irregularities in economic cycles. There could be a small political unrest, like in Fiji we had in the past decades, right? And but still things go on after a while. I mean, just recently we had a problem in Bangladesh. There was the Taliban taking over in Afghanistan, and a lot of other things happen. And of course, in Europe and Middle East, there's wars ongoing. So these are all things that are marks of developing countries. The other part in developed countries is they are stable, their borders are strong. You don't have the case where there's wars and invasions, and that's why the political system is sound and the economic activity is sound. So no stable trends, abnormal issues, and all those things are there. And the last point is that the historical data for Russia, there's lack of historical data for Russia in the data set due to the Soviet Union issue in 1991. So right, so how do we design these experiments? We had selected 13 countries in this PWT data set. Want to go and get the best model, and after the best model, we forecast the GDP using the recursive strategy. And what did we use in the experiment design? For all the deep learning models, we use the Adam optimizer, which is like a standard industry and academic standard, right? And we are looking at a multi-variate model. So we have 5 input units in those deep LSTM based models, and we are looking at the last 4 years, and we are predicting the next 3 years. So the next 3 years we are predicting using 3 output units. I would say that our framework is general, and this is the way we have implemented it. But you could also implement it in a such could have different encoder decoder style network, many to many architectures in the LSTM, where one model would predict the labor rate, the CPI, and all the other features at once. You could also implement it that way, but we didn't. Usually, having simple models is generally more preferred and gives better results. So that's why we took this approach. So the standard RMSE, IIC in the VAR model, we use the IIC as the error measure, and the standard, all the rest of the models, we use the RMSE. And some of the other details of the parameters in these models, the VAR legs. So the results for the first phase, we in our group we do overemphasize a bit in multiple experiments. So we are doing 30 experimental runs, which is the standard, the basic science you could do, which you wouldn't find in all machine learning papers. But we always try to do that. And you can see a wide range of models here. And we want to show people how these models behave both in the training phase and also in the test phase. So we first consider the case of Australia, and then for every step you are going to have its own RMSE from those 30 runs, and then there could be a mean RMSE of the steps. And then there's a case of Canada. I'm just putting these two close together because Australian and Canadian economy is quite similar in the sense. I mean, we have a Canada has a population of a little bit over 40 million, I guess, and Australia has 27 million, so around a 1.5 to $2 trillion economies. So those same results we are giving here, and for the different steps, for the different models, and basically those results tables are these figures are complementing those results tables. Why do we use both figures and tables in our papers? Is because in the future, when we develop better models, as I said, that we could change a bit of things in the framework, right? The framework is general. We could bring many to many LSTM models in there. We could also, if you do it now, then you could have data till 2024, and then you can make a prediction from 2025 to 2035. So we do similar things for the rest of the countries, and United States and Brazil, France and Germany, and so on, and India and Russia. Just the Chinese economy has been very has been of interest to the Western world for in the last decade because it's been doing very well, and generally people get concerned when a country does very well in a short amount of time, because doing very well meaning that if a country is doing very well in a short amount of time, that if your neighbor, forget about a country, if your neighbor is doing very well in a short amount of time and you are sharing the fence with your neighbor, then you would be concerned about, hey, are you making too much noise? I'm trying to sleep at night. You have too many parties now. But anyways, in a similar way, the case of China is very interesting, especially for the U.S. because of political dominance and and alliance, right? And we've seen similarly, we see that the prediction results are there for the train and the test RMSE, and the VAR model is usually not the best. In here, we see that the other models are also struggling. So we have 13 countries, 6 models, and it's good to basically have a simple figure that evaluates them all together. And this is what it does. It's basically a summary figure of all the models. And we see that the LSTM is doing quite good in the training set and the others as well, encoder, decoder, LSTM. Uh, but the thing about encoder, decoder, LSTM is doing quite well in the training, and it's also the best in the test. So that's why we consider the encoder, decoder, LSTM is the best model. And if you see VA and ARIMA, they are doing quite poor in the training and also in the test. And you have LSTM is not that bad, but you could see CNN is doing much better than the LSTM model, which is interesting because CNN is kind of meant for more for computer vision tasks, and LSTM traditionally people thought that they were more suitable for temporal data analysis, time series prediction models. But these days, you see CNN models are doing much better than LSTM for some very simple problems. And we are seeing similar trends in other applications of these models in hydrology, stream flow prediction, and cyclones, wind intensity prediction of cyclones, track prediction, and others. As a researcher in time series, I think CNN needs to be more and more utilized, and also the encoder decoder LSTM. Anyway, so there's a lot of models and a lot of experiments done. So we do need to have some type of a ranking. So we made a rank, and we have a average rank and a mode rank, and of the rank meaning that the lower numbers are the best. And as shown in the previous slide, the encoder decoder LSTM, here we see that that's rank number one. And the mode and average here is, it's good to report sometimes couple of indices, right? As here you have the mode and the average, because if we discretize this would become rounded. If we rounded off the average rank, this would become 2 and this would become 2, and basically we would be coming to a conclusion that the ED, LSTM, and CNN are both the same, right? But then the mode is kind of helping us to know this is better. And the previous slide, the individual RMSE of those basically shows that the ED, LSTM is better, right? So combination. So Rodney, you are there?
Yes, I'm here.
Right. I mean, could you take over this one, please? Then I will go. This is like,
Yeah, I think I can.
yeah, this is more of your area, actually. Yeah.
Yeah, so I think what we're looking at here is a variety of different uh, features or variables. So we've looked at net population growth, CPI, unemployment rate, and we've done some forecasts on those. This is for feature prediction because if you're predicting forward, you also need to predict the features forward. So that's what these results are reporting, and they're reporting basically root mean square error figures for the train and test data sets, and for different countries. So this is showing Australia and Brazil. CSH is the share in GDP per capita, and C represents household consumption. So these are basically component shares of the GDP, and G is the government consumption figure as well. One does need to be a little bit careful when inputting that sort of thing into the model as a predictor. But if you're doing it as a share, it's probably okay. Okay.
Yep.
Yeah, next slide, I guess.
I can take on from here.
Okay.
Thanks. So one of the limitations of our work is we have, because there's already a lot of results we had and there was a lack of time, but putting so many things in one paper is hard. So one of the other the limitations is that we have not really reported more analysis on the features that were predicted for the decade ahead, actually, right? And we did not do much analysis on it. One of the reasons is for the decade ahead prediction, it's hard to evaluate them because you do not know the future yet, right? So so we have shown the GDP rate visualization, but we have not visualized something such as the labor rate or CPI for the decade. So next we have a set of presentations about uh, how the Australian economy, for example, is going to increase. And this note that this is a snapshot of the world at the year 2019. That from 2020 to 2030, this is how the Australian economy is going to be, right? So I think if you look at the growth rate here, and this is kind of going mid 2025, and here basically it says that the growth rate will decrease more, right? And Australian economy is not doing that great actually in the last 2 years, and it may struggle in the year ahead. But our model would be enhanced further if we had the data, more recent data. But from the 2019 perspective, I think this model has done quite well in that sense. And on the other side, we have the GDP value. So we have the GDP, right? The GDP value of Brazil and all of these countries, Australia, Brazil, and you see this is Canada going down, and then it will go up for the case of Canada. China also struggling. Last 2 years, China has been struggling. Now Trump coming into power, right? That's going to have a bit of a issue with China and also India, because Trump is going to give some change the tax policy and other things for imports. So sorry, the title is incorrect. This is for France, and I think our model has been very positive about France. But if you look at France in the last couple of years, has been doing quite bad actually. And we have Germany next, and Germany, I think it's showing quite well in what's going on here. Germany is doing pretty bad at the moment for the last 2 years and this year, but our model is showing that later it will do better. And we have India. The case of India, we have India is sustaining its growth, and it's going to go worse. It's gone up, and this part I think for India is doing. Our model did quite well, but it is saying that India will get worse in the after 2025 to 2030. But according to all the IMF and other forecasts, that's kind of not true. It's going to maintain itself, but note that our data was from 2019, so that's what the model is showing. Then we have Italy, and it's just like Italy is going to really recover itself. Note that the y-axis is important. I mean, these changes does not really mean it's a huge change. It's 1 or 2%. So next is Japan, which is also struggling. Russia kind of maintained itself, but after the Ukraine war, Russian economy has actually improved due to dynamics around. And you have South Africa, UK. UK has been having a tough time, and I think looking at some of these predictions, it seems that our model has done quite well for the developed countries, right? And United States. I think this is a little bit. The case of United States is because this is still 2019, and that COVID came about and stuff. I say printing money out there. This is kind of considering that all those things were not done, right? So, but we are embracing for a larger economic growth in the United States. So, how do we compare with the IMF? How do we ensure that our model is done well? So we need to compare with some institutional forecasts such as IMF, and Lowley Institute also did it. So sorry with the reference there, but we have the model forecast of our and the IMF's growth. After that, we took the actual GDP and compared for the year 2027 what IMF gave. And the thing is that the IMF forecasts are not what the forecast IMF is given now. That's the IMF forecast of 2019, right, John?
Yeah.
So I just want to say that this slide was a bit of a headache for me and John and Rodney. The reason is what happened. This paper got accepted in IEEE Access very fast after it was rejected from another journal. I don't want to take any names, but it got accepted, and they were really happy with the paper. But we were not happy with this table, because the thing is that the general administrator asked us to fix a reference, and instead of IMF, we had the Lowly Institute reference. We gave a web link, and then we went to the web link. The web link was missing, basically. And then we're like, okay, how do we validate ourselves? And then we are trying to contact our first author, Tianyi Wang, and he's in China, and he's not checking his email because he's using WeChat now, not WhatsApp anymore. So these are some common things we have with collaborative research, some of the common limitations. So me, John, and Rodney, we sat for almost 3 hours, and we tried to figure. I mean, we were thinking about it for a day or two, then we sat for 3 hours, and then we went into the Lowly website, we went into the IMF, we started digging reports of what the world thought it would be in the future in 2019. And then finally we came to this IMF, and then this is the thing that we did change in the paper. And the problem with IEEE access is they will ask you to update a reference, but you're not allowed to change a reference. But we were just lucky that they accepted the change. It did. The thing is that it did not really change any of our conclusions. So if you look at this, our model did quite well for a number of countries. Japan did very well. China did very well. And Australia, it's okay. But Japan and China did really well. India kind of okay, close, but not that close like China and Japan. And Russia, not good. I mean, when you're looking at Russia and United States, we are looking at the war factor. But the difference, the worst that our model did, if we look at the IMF in 2019, was the United States, right? So, okay, so leave this to John. You wanna
Yeah, I'm happy to do that.
Yeah.
So one of the things that we didn't really talk about that much in the talk, because there's a lot of material to cover, is that the use of the shuffle training data, which is what Rohit was talking about with taking different windows and now analyzing that to avoid overfitting. Probably the surprising thing is that the encoder-decoder LSTM model was so useful in this particular task. And it compares not only did it have lower error in our independent test sets against the statistical models, it also compared quite well with the institutional forecasts. We were sort of, the model of the decadal approach is predicting a slowdown for most countries, which appears to have happened. And as Rohit was saying, it's predicting more stable results particularly for the developed nations, but also for China and India. We talked about 2019. Macroeconomic data is very limited. Like there's a lot more you could do with this approach if you had additional data or looking at longer time series. But nevertheless, we're quite pleased with the applicability of the machine learning to economic forecasting.
Thanks, John. So that brings us almost to the end of the talk. We have open source code and data as well. And this was done mostly by Tianyi Wang, and our data that's extracted from the PWT table, it's all there for the different countries you could see here, right? And you have all those features there. And we have basic code, which is the implementation of the LSTM model, and using Keras, and the LSTM model implementation is there. And we have model training and testing there. And that's the LSTM part, and then how this is being used to.
You did a big benchmark on this slide.
Yeah, there's a lot of things in this code here, because it's going into country by country. And so we have this code. It's basically doing for the different countries, the if and the else. I would be very frank to say that this may not be a really good coding exercise, because you shouldn't have ifs there. You should just have probably for loop, and you just change the country, and then you don't have to have such a large piece of code there. But it works, and it can be amended and implemented and improved. That's all we can say at this stage. And then you have some sort of accountability and transparency is here. So what we are going to do, of course, as you know that I'm not very happy with the code, we are going to extend the study further, and we are going to improve the code, and we're going to improve with the more recent data and explore other things. One of the things in future work that we would want to explore perhaps is um, other machine learning models. And as I said already, we get approach the many-to-many LSTM architectures, especially of the encoder-decoder architecture. And the other thing is that we would like to do is bring the variational inference part, so that we have uncertainty quantification in the prediction. And this is an example where uncertainties are really important. We want to examine how well they are quantified. We have a very limited data, very small data set, data problem, lack of data problem. And other things that can be done in the future with this type of stuff is bringing a multi-model approach. So we have been exploring multi-model approach with my collaboration with the University of Western Ontario. And I have a PhD student there, Masha, and we have a paper under review. It's about to come out about multi-model deep learning. So it's about predicting uh, credit rating of companies, of S&P 500 companies, credit ratings such as AAA, AA plus, those kind of things. And it's using a multimodal deep learning approach where it's text data combined with numerical data. So text data is all these companies, they have like some reports about how a company is doing. So there's like a couple of pages of reports, and then you look at the numerical data, which is some economic indicators of that company, financial indicators of the past of that country, similar to how we're doing at the GDP. So that is something that we could take that framework there, and we have evaluated a lot of models. There's 16 models, different combinations. And that paper is on archive. It's getting attention. And so we could bring those multimodal ideas in here and extend this work. So our group has a very small niche also of activities when it comes to finance and economics. And we have Dr. Rodney Beard, who is our economist basically. But we are going to carry on and expanding and working in this horizon in the coming years. Okay, thank you everyone. Any questions? Any questions for John? Or any comments? Rodney, do you have any comments you would like to add?
I just saw that Ethan Fan has had his hand up, so I don't know if he's got a question.
Right. Okay, Ethan. We don't see the Zoom app at the moment, so please you can ask the question, Ethan. All right.
Sorry.
Oh, you. Yeah.
Sorry, no question. I just clicked hand. So yeah.
Okay.
Okay. Thank you. Thank you.
Yeah, I'd have some things to add then. So two things when you're going through and looking at the growth forecasts to remember when you look at them, they're almost all of the growth forecasts are in positive territory, but you're looking at a growth slowdown, but they're all above zero growth rate, right? So just if you pick, any of the GDP growth figures like these figures here for India, you're looking at, go back India, yeah. So there you're looking at growth rate. The forecasts are showing growth rates roughly above 5%, right? So they're coming off a high at the end of 2019 of over 6%. So it's a slowdown. It doesn't mean the economy there is doing badly, right?
Yeah.
Yeah. So that's just something I'd emphasize. And then there was something towards the end I saw. I wanted to say something about.
But the case of Russia, it's like quite close to zero.
That's right. And they've been doing badly. You know, they were doing a little bit better before then, but they weren't doing really great, right? They're probably normal for a industrial
Yeah,
economy.
and they had this 2015
Yeah,
mess there in 2010 mess. So
yeah. And
yeah,
then the war breaks out and it all
yeah.
goes really
And
badly.
South Africa is the one that is the
Yeah,
problem.
so this is interesting because this is a developing economy and it was doing, but it's also got an industrial aspect to it. So it was doing pretty well, and then it collapsed basically with COVID, and it did, and well, we're forecasting it to collapse with COVID. Uh, Now, but we don't have the COVID data in here, so it's not captured.
Yep.
So this raises the question as to whether many of these economies wouldn't have done badly anyway going forward, even if COVID hadn't occurred, because we're actually forecasting that they do pretty badly. So the flat economic situation we're looking at now in many of these countries may have nothing to do with COVID, even though that's how people are interpreting it.
I think, Rodney, that's a very important thing that you have said, and it could be a paper on its own, right? Right.
Yeah,
Really, how much of impact COVID had, and which countries actually benefited from COVID, uh, taking into account decadal forecasts. And I think that even without developing any models, you could do some analysis just on the IMF's decadal forecast pre and post COVID and seeing what trends are there. And it's quite clear that some countries are doing quite well post COVID, actually. Yeah. And
yeah.
that's
I mean,
also,
some countries responded. The policy responses to COVID were quite good, really, right?
yeah.
So they softened the blow. So and some perhaps less so. But what we're seeing with our figures is because COVID plays no role here. We're saying if COVID had never happened, the economy in many of these places would have been slowing and would be flat, relatively flat anyway. So that's interesting because from this you sort of go back and then you look at what could we have doing something different with COVID wouldn't have made much difference perhaps, right?
Yeah.
Uh, yeah. Um, and yeah, and often these things are beyond control of policymakers anyway. Once
Yeah,
we
and I just want to
yeah,
say that in our Fiji Indian community, we do have a bit of a superstition about like if there's a bad event about to happen, we say that, oh, you're not, it's like the atmosphere becomes really bad before the bad event. It's like nature
yeah,
is trying to warn us. So that's a thing that we have in, and you don't feel good, you're feeling lazy, and something happens in your family or immediate family. You kind of have a sense, some kind of precognition, and kind of a superstition, we could say as well. Precognition slash superstition. But before COVID, 6 months before COVID, the world economy was behaving in a very strange way, I could say. It's like there
well,
was economic slowdown all around the world, and people couldn't explain why, actually.
well, China was slowing, but China also had other disease outbreaks at that time occurring, particularly with African swine flu, which affected the livestock prices. So, and then you had the sanctions that had been imposed. So there was the trade war basically that was going on. So a lot of these other things, potentially played a role in why we've seen economic slowdowns. Um, it's just interesting that we predict the slowdown, even though you know disease outbreaks weren't in the model, right? So
Perhaps the COVID had, I mean, less to do with things. Anyway, so we don't have any other questions or comments. Then we can end the session now, I guess, right? Um, I
yes.
thank everybody for participating.